Hello guys, welcome to Deep Codes, and in today's video we will discuss LeetCode question 785 that says, is graph bipartite? So guys, this question is very much interesting question and it is very fundamental question when you try to learn graph data structure. Also, towards the end of the video, I will tell you one another secret to solve this question. So yeah guys, stick till the end and watch the complete video. Here you are given one undirected graph with n nodes numbering from 0 to n minus 1. Further, you will be given a 2D array graph where graph of u is an array of nodes such that u is adjacent to. That means, let's say if you are given this graph of let's say node 1, so it contains the value, let's say n2, n5, n6. So this represents all the adjacent node to the node n1. Further, the graph has following properties. There are no self edges. See, so for a node u, there cannot be an edge to a node itself. So there are no self edges. Further, there are no parallel edges. So if there is a edge from u to v, then there must not be any another edge, right? So there are no parallel edges. Now, if a v is in a graph u, then u is in graph me. That means if v can be traversed from u, then u can also be traversed from v. Okay, so there will be some path between u and v because all the edges are undirected. So let's say if you have this node u and node v, and there is an edge between u to v, that means from u can traverse to v, and v you can traverse to u because the edge is undirected. Further, a graph may not be connected. That means the two nodes u and v, there can be no path between them. So let's say here one component of a graph is a, b and c. So this complete component is connected, and there is another component d and e. Now a and d are not connected because they are a part of different component. So the complete graph is not connected. Got it? So this type of thing can be there in the input. So this type of edge case can also be there in the input where the graph may not be connected. So we need to return whether the given graph is bipartite or not. So now what is the definition of this bipartite? It says if the nodes can be partitioned into two independent sets A and B such that each edge in a graph connects a node of a set A and a node of a set B. So guys, this means that for every edge, let's say for edge between node 1 and node 2, the node 1 must be of a set A, node 2 must be of a set B, and this must be valid for every edges of a given graph. That means all the nodes must be partitioned either in set A and set B such that for each edge one node must be of set A and another node must be of set B. If this condition satisfies, then we can say a given graph is bipartite and return true. So let's see the given example for better understanding. Okay, so here we are given this graph. So let us try to divide the nodes into set A and set B. So let's say we added the node 0 in a set A. Okay, then let's see for its adjacent. If this is in a set A, then this node must be in a set B, correct? Because there is an edge for each edge, one node must be in a set A and another node must be in a set B. So this must be also in a set B, okay, and this must be also in a set B. Got it? If this is a set A, then all these three nodes must be in a set B. Now if you see this edge, is there any conflict? Yeah, there is a conflict because both the node of this edge are of same color, and that is false, right? That is not true. So this must be either red for this node, for these two nodes to satisfy. For this edge to satisfy, this node must be of a red color, but then there will be conflict from here. So guys, there is no way to divide all the nodes into two sets, either set A or set B, such that each edge has a different colored nodes or a different set nodes. So it is not possible here. So that's why here we written false here, because there is no way to partition nodes into two independent sets such that each edge or every edge connects the nodes of one edge in another, right? So this is not possible here. Further, if you take a look in this example, so let's say you partition this node into set A, then let's say you added this node into set B, you also added this node into set B, and at the end you added this node in a set A again. So here if you can see, let's take an example for this edge. Both the nodes are of different set, correct? This edge, both the nodes are of different set, correct? Different sets, different set. So every node has an edge from a set A node to a set B node, right? So this complete graph we can say is a bipartite graph, and that's why we return true. Yeah, right. We can partition each node into two sets, set A and set B. So yeah, guys, that's why this is we return true here, because they satisfy all the condition. So yeah, guys, I hope you that now you have somewhat understanding that what we are trying to do. We are simply trying to partition the node either in a set A and set B, such that every edge of a graph connect a node from a set A and a node from a set B, right? For each edge has a node of two different sets. That is what we have to satisfy. So guys, just think of it that dividing these two sets can be simple as like coloring the graph with two colors, right? Coloring the graph, that means coloring each node either with a color 1 or a color 2. So what we can do is we can make sure that adjacent nodes are of different color. That only we have to make sure, because what is an edge? Edge is nothing but between two adjacent nodes, that is there would be one edge, right? And so if we make sure that the adjacent nodes are of different color, then the condition is satisfied. Then we can say that for each edge there is a node of a set 1 and a node of a set 2. So guys, you can think of dividing these two sets A and B into coloring 2. Let's say coloring with red and blue. So we can color each node either with a red or a blue. That means each node can be either be a part of a set A or a set B. So yeah, and let's try to make sure that the adjacent nodes are of different color. So if the adjacent nodes are of different color, then we can say graph is a bipartite, right? Because for each edge, for every edge, there if the adjacent node are of different color, then we can say there is a edge between a set A node and a set B node. So yeah, we have to just try to do this. Adjacent nodes are of different color, then we return true. So for an example, let's say this node we color with a blue. Okay, then these two nodes must be colored with a red. Okay, correct. And this node can be again colored with a blue. So yeah, the complete graph satisfy the condition that the adjacent nodes must be of different colors, and yeah, we return true for this example. Now if at any step we find two adjacent nodes are of the same color, then at that step only return false. If at any point of time if the two nodes are of same color, then return false. Let's try to trace this. So for an example, let us color this node with a blue. So we color this node with a blue. Now the next thing we can do is we can color the adjacent node with a red. This has a red, this has a red. Okay, now let's say we try to color the adjacent node of both these nodes as a blue. To satisfy this edge, we have colored this as blue, we have colored this as blue. Now whether the condition satisfy for this edge? No, these two adjacent nodes are of same color. So does this condition satisfy? No. See, first we try to satisfy this condition for this edge and this edge, for these two adjacent nodes. Then we try to satisfy for these two adjacent nodes. But after doing this, we found out it is nowhere possible to divide these two nodes into different sets, right? It is nowhere possible. So at this case, we will simply return false, because it is not possible to divide the nodes into different sets. Okay. So yeah, guys, here we simply would try to do what? We simply would try to color each node. So what is this coloring technique and how we will perform them? Yeah, we can simply perform them by traversal. We are simply traversing starting from one node to every other node. See, as we did here, we started traversing from one node to each other node. So that can be either done by BFS and DFS, and we will discuss both these techniques. Now here we are talking about coloring. So how we will color them? So we will maintain one array where 0 would mean it is not colored, 1 would mean color 1, and -1 would mean color 2. Simple it is, right? Now let's talk about BFS approach. Okay, so firstly we would check, let's say starting from node 0, we would check whether the node 0 is colored or not. So if it is 0, that means it is not colored. So let's try to color them with a colored one. So let's try to color it with a colored one. Okay, now we would since this is BFS, we would check both the adjacent nodes of a node 0. So we would find that is the node 2 colored, node is not colored. So we will color the adjacent node of a node 0 with the opposite color. That means if this is colored with a +1, we will color it with a -1. Okay, we would color all the adjacent of node 0 with -1. That means nothing but with a blue color. Suppose, see, blue color as we are talking here for -1. Now further check whether the node now we will check adjacent of, let's say adjacent of 2, whether the adjacent of 2, that is node 3, is colored. No, it's not colored. So color it with a color 1. So that means color it with a red color. Okay. Then check for the adjacent of node 1, that is node 3. Is node 3 colored? Yeah, it is colored. Then again check whether it is colored with the opposite color of a node blue. Yeah, it is colored with the opposite color of a node blue. Then yeah, we are good. Then it's okay, right? Since the adjacent nodes are of different colors, it is okay. Okay, now move forward. Now take the node 3 as the current node and check for adjacent of node 3. Okay, so adjacent node to a node 3 is a node 4. So, and this is colored with a color 1, so color it with a color -1. Got it? So yeah, we color it here. Now then check for a adjacent node of a color of the node 4. So there are 5 and 6 and they both are not colored. So simply color with the opposite color of a node 4. That means color it with a red. Got it? Now afterwards no nodes are remaining. So yeah, at the end we return true. We return true since no nodes are remaining. Now in the same example, let's say in the same BFS technique, if there would be some graph like this. Okay, let's say there is some graph like this. Let us quickly try to make a BFS call. Okay, colored this with a red color. Now check for the adjacent. If are the adjacent color? No, they are not colored. So color it with the opposite color. Correct. See what we did. We colored this, then we check for adjacent. They are not colored, so color them with the opposite color. Now let's say this is the current node. Node 2 is a current node. So adjacent is this. That is not colored. So yeah, try to color it. So let's say we color it with the opposite color, that is red. Okay. Now let's say in our queue we have node 1. What is this adjacent? This node 3 is our adjacent. So it is not colored. So color it with a different color. 3. Now let's say in our queue we have node 4 and the adjacent node is 3. That is colored. Is this colored by the same color? Yeah, it is colored by the same color. So is this valid? No, it is not valid. So for this condition, we would return simply false. So we would also check whether the adjacent node is colored or not. If it is colored, then we would check what is the color. If it is same as the parent node color, so here we are traversing from this to this node. So this is the parent of node 3 and we would check whether the node 3 color is the same as the parent. Then yeah, it is a false. It is an invalid condition. So at that point, we would return false. So yeah guys, that's how BFS approach or BFS traverser will help us to find whether the graph can be divided into two sets A and B or not. So yeah guys, let's move on to the coding part. The coding part is very much simple here. So first what we did is we took with this outer for loop. Why? This is because graph can be disconnected. That means that can be more than one component. More than one connected component. So yeah, that's why to traverse all the connected components, let's say component 1, component 2, all these components, we would take this outer for loop. Now inside this for loop, we are simply doing what? We are simply doing breadth first search. So for that we took a queue and this color array. So 0 means unvisited, -1 means color 1 and 1 means color 2. Whatever you say, +1 means color 1 and -1 is color 2, whatever you can take. So if a node is already colored, then we would simply continue. As what we would do is we would take one queue, we would start our BFS, add the node into our queue and color the node with a color 1. Let's say we colored it with a color 1. Then we started this while loop where we would traverse the nodes that are stored in the queue. Take the current node and traverse all the adjacent node of a current node. Now we would check if the adjacent node is colored or not. So if it is not colored, simply color it with a different color of the current node. See, this is the current node. This is the current node and let's say n1 is adjacent node. So this adjn is nothing but n1. Now if this is not colored, so simply color it with the opposite of a color of a current node, right? So yeah, we are simply doing this. If it is colored with a, let's say if it is colored with a red, then we are coloring the adjacent node with a blue. Got it? Else, this is the condition we have to check. If the adjacent node is colored, then we would check what is the color. If the adjacent node color is not equal to minus of color of a current node, that means this means what? Color of adjacent node equals to color of a current node. If this condition hits, if the adjacent node color is equals to color of a current node, then return false, right? So this is nothing but if you remove this not equal, okay, so we have changed the condition to this. If the adjacent node color is same as the color of a current node, That means two adjacent nodes are of same color and this condition is a false. So yeah, return false. So yeah guys, I hope you understood the BFS approach, that we are simply taking one node, starting from one node and trying to color the adjacent node, and if at any point we find that the adjacent node is already colored and the color is same as the current node, then in that case we return false. Yeah, as we did here in the else if condition. Now the DFS approach is no more different, it is almost the same, only thing is we are trying to do DFS. Let's quickly see this. So for suppose, let's say this node is colored with a color 1, then it's adjacent. Since we are doing a DFS, we will traverse across the depth. So this node would be color of a different, then the adjacent of this would be color of something different, then the adjacent of this node should be color something different, then the adjacent should be color something different, and this should be different. Okay, and at the end, yeah, what is so this will make a reverse call. See, DFS makes a reverse call, right? Here, here, and here. Now we will see that one more adjacent to node 0 is remaining. Okay, so let us color it with blue. Now after this, we would check adjacent of node 2. We would check that adjacent of node 2 is node 3, whether it is colored with the same color or not, whether this node is colored with the same color or not. No, it is different. So yeah, we are good here. So we would check that condition at each stage if the adjacent node is already colored, and we would check whether it is of same color or not, and based on that we would return true or false. So this DFS is no more different. We have taken this outer for loop so that we cover all the different components of a graph, and then inside that we call this valid coloring. This is nothing but a DFS call. So here we pass the graph, the color vector, the current node, and 1. Okay, so 1, that means we would color the current node with a color 1. So yeah, we would color it, then we would try to find all the adjacent node of the current node, right? And we would check if the adjacent node, if it is colored with a different color, that means if this is 1, and then if it is colored with a -1, we would check recursively. So yeah, that color of the adjacent node is not equal to 0, that means it has some color, and whether if that color of the adjacent node equal to this color that we want, this is the color that we have passed, that color we want. Okay, so if it is same, then yeah, we will return true. That means the graph is valid. Okay, this means the graph is bipartite. True means it is bipartite. See, here we are itself changing the color. If this is of a, let's say if the current node is of current color, then we are passing minus of current color. So if it is 1, then we are passing -1, and we check if the color is -1, yeah, then we return true. We are good here. Now if it is color 1 and we are passing minus of -1, that means it is 1. So yeah, if this is the case, then we would return false. Okay, simple it is. So this DFS approach is no more different here. Now talking about the time and space complexity. The time complexity of both this DFS and BFS approach is nothing but big O of n plus c, that is number of nodes plus number of edges, and space complexity is number of nodes, as we are using this color vector in both the approaches. Now guys, what one other observation that you have to take here, or what is one secret here, is a graph, if the graph contains an odd cycle, then it's not a bipartite. That means if a graph don't contain an odd cycle, then it is bipartite. So if you take any graph, let's say A, B, C, so this graph contains an odd cycle. See, the cycle has odd number of nodes, right? Then this can never be a bipartite. And if you have any graph, let's say A, B, C, D, and E, okay, so this graph has this cycle. See, this is a cycle, and this cycle is even because it has even number of nodes. So if you have this type of graph, then it will always be bipartite. So yeah, to check a bipartite, if a given graph is bipartite or not, you have to check only one thing: does it has an odd cycle? If it has an odd cycle, then return false. If it doesn't has an odd cycle, then return true, right? So if a graph don't have an odd cycle, then return it is true. Then the graph we can say it's a bipartite. So yeah guys, this is one secret or observation that you can take from this question, that if a graph contains an odd cycle, then it will never be a bipartite, and in all other situation it is always bipartite. Take it as a take it as a fact, right? So yeah guys, that's all for this video. If you find this video helpful, then then make sure to like this video. If you still have any doubts, then do let me know in the comment section. So yeah, like the video and subscribe to our channel. Thank you.